Katz Water Technologies. We want to, like everyone else in this room, help solve the world's water problems. In particular, help industry recycle their energy and water. So we talked about some of the customer problems. One big problem is gas flaring. Billions of dollars of gas is being wasted through venting or flaring because there's no pipeline or market. You can see areas like the Bakken in North Dakota and West Texas are as well lit up as major cities in satellite photographs. Another problem is seismicity concerns. As we increase volume and pressure, we see an increase of earthquake. This is from the U.S. Geological Survey showing an increase of earthquakes. Recently, Oklahoma has shut down quite a number of disposal wells, and Texas is now spending millions of dollars studying the problem, and recently shut down for the first time 2 disposal wells, so it's becoming a bigger problem disposing the water in deep water disposal wells. This we spent a lot of time talking about fresh water stress. You can see in the map regions where there's quite a bit of fresh water stress also overlap with many of the major oil and gas production zones. And oil and gas is competing with municipalities, farmers, and ranchers for scarce fresh water use. So our solution is to recycle the wasted energy as well as the wastewater and create a new circular economy at the well site. So I'll talk a little bit about technology. Usually I'm told talk too much about technology, but since this is a technology group, I could probably get away with it. So our patented solution or enabling technology is what we call the XFAB, and it's the ability to do the entire thermal distillation process inside a heat exchanger. This drastically reduces the cost to build the equipment, the cost to operate it, because we're only operating one process step instead of several in traditional thermal distillation, as well as the thermal efficiency. Since everything is done in the heat exchanger, our thermal efficiency is the thermal efficiency of an industrial heat exchanger, which is typically above 90%. In addition, we've also engineered it to take advantage of pressure as well as a surface area. So people say, are you a multi-stage flash or what are you? We're probably a hybrid between a thin-walled distillation process and a multi-flash system. So we've also solved a scaling problem by making it a continuous throughput system. The water spends anywhere from 8 to 12 seconds, and we've also made it easy to remove the inside distillation column. So if we do have scaling, we can clean it up very rapidly. And the material for the distillation column is high strength, is a very corrosion-resistant stainless steel. So here's a process diagram. We have our energy source. The good thing about our system is energy agnostic. So in this process diagram, we're either showing flare gas that is being sent through an integrated gas burner or solar thermal, which we send through the heat exchanger. We can also use industrial waste heat energy. We run it through our heat exchanger that's been modified to do the entire thermal distillation process, including the heat exchange, the distillation and separation, and we get our pure water and our brine, as well as we use energy recapture on the brine to preheat the water and improve the mass energy balance. So once we built our first prototype, we took it to a well site in Spring, Texas, right outside of Houston, and we ran our system. And we were able to achieve over 99% TDS removal. In this, you can see the elemental analysis. That is roughly 100,000 TDS produced water, and we got it to well under 1,000 TDS. What's interesting is we're pretty much removing 99% of the elements across the board. The reason why we're not getting 100% is mostly because of the property called entrainment. The vapor has enough energy, it's going to carry some of the contaminants with it, and when we condense it. You can see the picture of the produced water, the heavy brine, and the vapor. So what we're proposing to the oil and gas customers is to create a new circular economy. We're going to take the produced water. The key is to do it less than the current cost of disposal. We're going to integrate our system through their pre-existing water infrastructure, because that's very expensive. Run it through our XVAP system, and then we're hopefully going to create two revenue streams. We have the water that we could resell as industrial process water or reuse on the well site or agricultural water, as well as the heavy brine, which in some instances, because of the density we're getting, could be used as a base stock for drilling mud as well as completion fluid. If we can't sell the brine, then it'll have to be sent to disposal well, but that still drastically reduces the cost and the volumes, which will reduce the seismicity problem. So this is our field trial, what I mentioned that spring. We put 3 of them in this trial in a trailer. It's a simple and transportable system that we roll up right to the well site. We hook it up directly to their storage tanks, and we gravity feed the water in this situation. You can see it's a simpler modular design. That's 18 of them in that same trailer. And unlike other technologies, we definitely scale linear, and we're hoping to do better than linear by having economies of scale, by mass producing, and cost efficiencies by only having one SCADA system and pumping. We've also built a SCADA system so we can control it completely by remote control, so that someone in Houston can control everything remotely, so we don't have to have an operator on site. I mentioned the test samples, and we've proven this at the well site by directly connecting it to the water handling system. So the competition is mainly disposal wells. As far as other treatment technologies that have been tried at a large scale, Veolia has a thermal distillation system. They tried that in Marcellus. That recently closed down. And Gradient had a system out in West Texas that was also closed down because the economics didn't work. So we did a comparison of Veolia systems, so they're still trying to sell it. As you can see, they use traditional thermal distillation. There's several processes. You have your energy source, electricity, your heat exchangers, your distillation, your separation, and your and that's all a separate process step. That's replaced by one piece of equipment. You can see we're orders of magnitude cheaper to build, to operate, and a lot less footprint. So this is the market. I'll say it's a very large market, about $35 billion, and just capturing a few dozen well sites a year, small well sites a year, could lead to a very profitable revenue stream. So in this video, now initially we thought the oil and gas customers are going to want the water because it makes sense. They're using a tremendous amount of water. They're operating water scarcity. What we're finding is they don't want the water, mainly because of regulatory concerns and liability issues. So they just want the problem to go away. And apparently it's easier to vaporize it into the atmosphere. It's easier for them to get an air permit than it is to get a water permit for reuse. So basically we have to do what the customer wants, so we're focusing a lot on evaporating it and not condensing it. Here's a rendering at 60, so we can increase the number. So obviously there's thousands of barrels being produced, so they want to increase it. So this is 60 in a SolidWorks rendering. We even have designs that put 120 in a standard shipping container. So we're also working on solar desalination. We've been funded with the U.S. Air Force, which wants small portable systems, as well as the DOE through their solar desalination. We were a quarter finalist and then a semi-finalist as part of the program, and both have been very helpful. So we redesigned it to hook up to a closed-loop solar thermal. This is what we're building for the Air Force. It's actually built. We're waiting to, we just started testing with our solar thermal parabolic mirror. We put 6 on a skid, so it'd be easy to mount on transport by a truck. And then we're planning to hook it up to a solar thermal parabolic dish. We ordered 2 from Rockham. They've been delivered. Unfortunately, we're working with Rockham on fixing their alignment issue and hope to have that fixed very soon so we can start testing and eventually bringing it to a U.S. Air Force to desalinate water. But as you can see, the dishes are small, portable. We could fit several of them, one of them in a truck and several of them in a storage container. We also have a map showing the solar irradiance. What's interesting to note is the highest levels of solar irradiance in the US, some of the highest numbers in the world are in the Southwest, and that's really where most of our water scarcity issues are. So eventually solar desalination would be a perfect technology to solve the water scarcity issues in the Southwest. So for the DOE, we're planning a larger demonstration of 100 cubic meters per day versus a small system for the Air Force for remote bases. So here we have 60 of them in a storage container. We've also switched up our condensation to a modified shell and tube heat exchanger that we're building locally. And this could do approximately 10 cubic meters a day in the Southwest using average solar irradiance. This is a process flow diagram. It would be a very simple system where we have the input water and we have from our feed tank, we run it through pumps through our condenser. As we condense the water, we get the heat from both the vapor and from the brine. We preheat it almost to distillation temperature, and then we run it through our system, and it's connected to a closed loop solar thermal array. So initially we were going to do it at Alamogordo here locally. So we did a satellite plot diagram of where it would look, one trailer hooked up to the water tanks, the feed tank, the brine tank, and the fresh water tank, as well as the condensation and solar array. So this would be one trailer hooked up to 10 solar thermal parabolic dishes, each doing 10 kilowatts, so a total of 100 kilowatts. Based on the DOE, they suggested we do it at a customer site. So we're talking to a major company tomorrow with 2 of their contractors to do a solar desalination plant. And what we're going to do is look into doing a hybrid where we could run it by natural gas through a gas furnace or through the solar thermal, so we're energy agnostic. And then we did a New Mexico field trial. Fortunately, we ran into some problems. I'll briefly discuss it. One of the problems is we had a small feed tank, so as the height adjusted, we ran into, when it was low, we had to run a pump versus gravity feed at the well site. And when it got very high, when it was refilled, it overwhelmed our pump, and we had to fill up our system, and the first time ever we had scaling issues. So now we have an automated tank level control that could either turn on the pumps when needed, or pressure, or choke down the pressure. We also, when we switched to propane, because there's no natural gas here, we had some exhaust problems. So we had to redesign our exhaust system. So we're also working on metals removal. I think I'm out of time, so I won't discuss it. One of the benefits with the DOE, with the DOE prize money, we created our own machine shop so we could rapidly prototype. So now we can prototype in days versus weeks. We have a great team. We've been funded with quite a bit of federal grant money, and recently we got a contract with a major midstream. I can't mention their name because they're on their NDA, but many of the people know who they are. Go figure, they could talk about it, but I can't. Oh well. So I said I wouldn't mention most about our patents, but we've been heavily patented. We have 13 issued, another 14 pending, and I think I'm out of time, so I'll have to answer questions later.